Greetings, it is I, Mr. Burkhart, still making these videos. I hope somebody cares. Carlo pushes a block of mass M across a rough horizontal surface at a constant speed by applying a force F directly to the right. Thank you, Carlos, for moving that rock. The dot at right represents the block. Draw a free body diagram showing and labeling all the forces, not components, exerted on the block. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Right. Carlos is pushing. This is called push. Okay, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. This would be friction. And they're equal because, it says right here, constant speed. Constant speed means A equals 0. If A equals 0, that force equals 0. So all the forces have to be balanced. So let's say that we have a force of gravity, 1, 2, 3, 4, 5, 6. That's how they write it in AP Physics land. I usually write FG, force of gravity. And then 1, 2, 3, 4, 5, 6. This would be the normal force, not the natural force. They're all natural. They're all 100% natural and organic. But it's a normal force because it's perpendicular to the ground, not the mg. It's not perpendicular to these forces. It's perpendicular to the ground. And in Britain, they call that a normal situation because they're weird. We start with Newton's second law, which says that the sum of all the forces exerted on an object is equal to the object's mass times... what am I supposed to do? Blake is asked to use Newton's second law to derive an equation that relates the force of gravity and the normal force from the surface exerted on the block. Annotate this derivation by filling in the right side of the table below. For each line of the derivation, explain in words what was done mathematically. The first line is done for you as an example. Okay, the net force equals mass times acceleration. This is just in the up-down direction. So the two forces in the up-down direction are the normal force and the force of gravity. So the normal force is up, so positive. Force of gravity is down, so negative. And the sum of, I spelled that wrong, sum of the forces is always equal to the mass times the acceleration. That's where it comes from. We have the net force. This is the net force. It's the sum of the forces. All right. The acceleration is 0 because forces are balanced. Right? They're not. It's not moving in the upward direction. Not moving up and down. It's not moving up down. So if A is 0, this is equal to 0 because 0 is equal to 0, I guess. Whatever. And what we do is we added a force of gravity to both sides. All right, 3 minutes. Part C, page 2. Carlos gets tired of pushing, I'll bet, and begins to pull because that's different. With a force F pull at an angle to the horizontal, the block slides along the rough horizontal surface at a constant speed. A free body diagram for the situation is shown below. Blake makes the following claim about the free body diagram. Okay, we have a free body diagram. The velocity of the block is constant, so the net force exerted on the block must be 0. True. Thus, the normal force equals the weight. Nope. And the force of friction equals the applied force. Nope. What, if anything, is wrong with this statement? If something is wrong, identify it and explain how to correct it. What happened? Oh, I got an email. I'm ringing my ears. What's wrong? All right, so what's wrong is the normal force is not equal to the weight, and I'll tell you why. So you can see here that this force is pulling up and sideways at the same time, right? So it's pulling up, so the normal force plus the component of the pull that's in the y direction is equal to mg. Right, these two. This thing is helping the normal force. It's taking some of the load off the normal force. So we have this is pulling up, and that's the normal force. Those are both pulling up, balancing mg, because it's still not moving in the up-down direction. So this is actually the true statement, that the normal force and the vertical component of the pulling is equal to the weight. So that's no bueno. The force of friction equals the applied force. Also, no. Force of friction is not equal to F pull. The force of friction is equal to the component of the pulling, which would be F pull times the cosine of that angle. Right? And this would be force push sine of that angle. Right? There's an angle here. This would have components. They really hate it when you draw components. So here's a checklist. I'm sure I did it great because I'm amazing. I'm at 5 minutes, 5.5 minutes. And part D is all of this stuff here, which I'm sure is going to take more time. It's going to make it a long video. So why don't we just stop this one?